Hello, my amazing students. This is Mrs. A, and we are starting 6.1, and we're starting to talk about the normal distribution. So hang on. Okay, so chapter 6, we're starting to talk about the standard normal distribution. I'm going to try to be doing videos of each section for you as we are just getting into such a critical time with the end of the course getting nearer, and we just have to make sure that everybody can thoroughly cover each one of these concepts. So I'm still going to go over them with you in class, but in case you're unable to attend, or in case we do not get all the way through the material, you're going to have it here. So now we're talking about the key concepts here. A standard normal distribution is bell-shaped, and it is got a mean of 0 and a standard deviation of 1, and we're going to be talking about that standard normal. But that's not the first thing we go into here. First, we'll talk about just the normal distribution as opposed to the standard normal distribution. A normal distribution is if a continuous random variable. Now remember, last time we were talking about probability distributions and then binomial probability distributions, and those were both discrete distributions, and now the normal distribution is continuous. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution. This is the equation for the normal distribution. You do not have to memorize that. And then this is the shape of the normal distribution. It is bell-shaped and symmetric. Okay, now we're going to talk just a little bit about a uniform distribution, because they're trying to just cover all of the continuous distributions, and the uniform distribution is the first one that they cover. So you'll see in your book that they start first off talking about the uniform distribution, and the area under the graph of a continuous probability distribution is equal to 1. That's going to be true for every continuous probability distribution, including the normal. The standard normal and the uniform. There's a correspondence between area and probability, so probabilities can be found by identifying the corresponding area in the graph using the formula for the area of a rectangle. So area is height times width. Looks like that got cut off a little bit. There we go, I got that one fixed. Okay, so the area of each rectangle is the height times the width, and the area will also equal the probability, and the probability will equal the area, so vice versa. Okay, so uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over a range of possibilities. The graph of a uniform distribution results in a rectangular shape. So we're about to see one of those in just a minute. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. So here you're talking about the correspondence between area and probability. So here we have an example. It says waiting times for an airport security. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes, as illustrated in the figure on the next page. So this is a uniform distribution. Okay, all of the different possible waiting times are equally likely. Okay, so then it says waiting times can be any value between 0 minutes and 5 minutes. So it is possible to have a waiting time of 1.23456 minutes. Okay, by assigning the probability of 0.2 to the height of the vertical line in the figure, the enclosed area is exactly 1. Because you have, down here, you've got 5 different time slots. And 5 times 0.2 is going to be 1. So we have to have the area and the probability equal to 1. So then it says, given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. Okay, well, at least 2 minutes would mean 2 minutes, 3 minutes, 4 minutes. Okay, so since we've got 0.2 and then we've got 3 time slots that we're talking about, it's going to be 3 times the 0.2, which should be the 0.6. So a 60% chance that you will wait at least 2 minutes. Again, this is a uniform, so everything is equally likely. So it's just an area consideration here. Okay, the probability of randomly selecting a passenger with a waiting time of at least 2 minutes is 0.6 or 60%. All right, so now we're going to leave off on the uniform and move to the normal distribution. Okay, continuous random variable has an infinite number of possible values that can be represented by an interval on the number line. So here we have something continuous, which is hours spent studying in a day. Okay, the time spent studying can be any number between 0 and 24 theoretically, although I really doubt anybody could study for 24 hours straight, but maybe you're amazing like that. So continuous probability distribution, the probability distribution of a continuous random variable. Okay, like I said before, the probability distribution that we did in the last chapter was discrete. This one is continuous. Okay, the normal distribution is a continuous probability distribution for a random variable x, the most important continuous probability distribution in statistics, and the graph of the normal distribution is called the normal curve. You will also hear it very often called bell-shaped. Okay, the mean, median, and the mode are equal in the normal distribution. The normal curve is bell-shaped and is symmetric about the mean. The total area under the normal curve is equal to 1, as it must be for all uniform distributions, or all continuous distributions, let me say that. And the normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. So it's coming down here and it's getting closer and closer, but theoretically it never ever touches. And the total area is 1. Okay, so properties of normal distributions. Between mu minus sigma and mu plus sigma, which is going to be your 1 standard deviation from the mean mark here, you're going to have approximately 68% of all of your data points. Okay, remember that from the empirical rule. But here they're giving you something a little bit different. They're saying the graph curves upward to the left at this point, at the mu minus sigma. So that's the 1 standard deviation mark negative, 1 standard deviation mark positive. You have these inflection points. So they're saying that's where it changes from curving downward to curving upward, is at those inflection points. A normal distribution can have any mean and any positive standard deviation. The mean gives the location of the line of symmetry. The standard deviation describes the spread of the data. And here, notice that they're showing those inflection points here. And those are really not going to come into a great deal of play here. Don't worry about those a huge amount. But notice that this one has a mean of 3.5. This one has a mean of 3.5. And this one has a mean of 1.5. Okay, so the means of these two are the same. But look at the standard deviation. The standard deviation is very spread, but here it's very close together and tight. So these two have the same mean, but these two have the same standard deviation and different means. Okay, so here they're showing you the means and the standard deviations of each. These two both have a 0.7. The smaller the standard deviation, the more piled up your points are going to be, and your curve's going to be narrower and sharper and pointier. The wider your standard deviation, the smoother and lower your curve is going to be. Okay, which normal curve has the greater mean? Okay, now the mean is the center of the data, so A has got a greater mean because it is farther to the right. Okay, and then it says curve A has the greater mean. Which one would have the greater standard deviation? Okay, the greater standard deviation would be B because it's more spread, and a wider standard deviation is more spread. So A has a smaller standard deviation. Okay, so it says greater standard deviation, that would be B, and curve A has a smaller standard deviation. Okay, so here we have an example. The scaled test scores for the New York State Grade 8 mathematics test are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? Estimate the standard deviation. Okay, so we got to get a little bit closer here. So the mean is going to be somewhere here, right in the middle, right underneath the peak there. So maybe, let's see, 650, that looks like it's broken up by tens there. So 675 or something like that. Okay, let's see what they said. 675. Okay. And we're supposed to estimate the standard deviation. Okay, well, when you're looking at something this and you're just looking at it from the graph, we could estimate the standard deviation by estimating where is that inflection point. Okay, so they're showing you where they're thinking the inflection point is, because the inflection points are one standard deviation from the mean. You can estimate that the standard deviation is about 35. So you're looking for the place. You're saying, okay, where is it changing from downward to upward? And if you can notice some change here, so like right between here and here, it's just pretty much a straight line. But you can see that right here, yep, you're starting to see it curve down. And over here, you're starting to see it curve up. And so you get that straight line portion there, and you kind of go halfway in between it so that you can estimate where that inflection point is. Okay, so here, standard normal distribution. So now we're moving from normal to standard normal. Remember, normal can have any mean and any standard deviation. A normal distribution has got a mean of 0 and a standard deviation of 1. So it's special. Okay, it's got more requirements here. So any x value can be transformed into a z-score by using this formula. So we got the value, the x value we're talking about, minus the mean divided by the standard deviation will give us the z-score. The z-score is how many standard deviations are we from the mean? Okay, so we can take a normal distribution that has a mean that's not 0 and a standard deviation that's not 1, and we can turn it into a standard z-score by finding this formula. Okay, so here we have, if each data value of a normally distributed random variable x is transformed into a z-score, the result will be a standard normal distribution. Okay, so here's a nice little picture. Okay, so we have a normal distribution that right in the center is a mean, any mean, and a standard deviation. Okay, and now we're going to use this formula for the z-score, and we're going to transform it into a standard normal distribution with a mean of 0 and a sigma of 1. Okay, so it's our z-score that does that for us. Use the standard normal table to find the cumulative area under the standard normal curve, and the cumulative area is also the probability, which we'll be talking about quite a bit. All right, so properties of the standard normal distribution. The cumulative area is close to 0 for z-scores close to negative 3.49. So basically, effectively, remember, theoretically, this continues on and on forever, but we're going to say theoretically the area is very, very close to 0, and we're going to say if we get a z-score negative 3.49 or greater, we'll say that area to the left of that is 0. if we had a positive 3.49 on this side, we'd say that the area to the right of that is 0. The cumulative area increases as the z-scores increase. Oh, that was fun. Let's do it again. Okay, so you see how cool that was? The cumulative area increases as the z-score increases. So the area under the curve is 1, okay, and the area under half the curve is 0.5. Okay, so the cumulative area is close to 1 for z-scores. So basically, if you're getting all of this all the way over here to 3.49, you're going to assume that this area here is 1. All right, so we can find areas which are the same as probabilities for different regions under a normal model using technology or the table A2. Now this is in your book, so your book has A2 in the back, and we're going to use that a little bit. Technology is strongly recommended, and we are going to use that also, okay? If using A2, it is essential to understand these points. Table A2 is designed only for the standard normal distribution, which is a normal distribution with a mean of 0 and a standard deviation of 1. Table A2 is on 2 pages, with the left page for negative z-scores and the right page for positive z-scores, and each value in the body of the table is a cumulative area from the left up to the vertical boundary above the specific z-score. So we're going to see some of that in just a minute. Okay, we're just looking for, he says, when working with a graph, avoid confusion between z-scores and areas. Z-score is the distance along the horizontal scale. It is the number of sigmas or standard deviations you are away. Okay, the number of standard deviations you are away from the mean. It's corresponding there. The area is the region under the curve, and it is also the probability. So it is the values in the body of the table. And then number 5 says the part of the z-score denoting hundredths is found across the top row of the table. So let's look at some table values here. Okay, now this one is just an example. I'm going to show you the back of your book, A2, real quickly. All right, so this is the negative z-score. This over here is the positive z-score. These are the tables that are in the back of your book. This is A2. So we have the negative values and the positive values here. So when we're looking at this, if we're going to look for a z-score, say we wanted to know, remember, this is normal, standard normal, so -1 to, let's look at this, -1 standard deviations right there. Okay, so -1 is right there. And we're going to say -1.00. So I've got 0.1587 is the percent to the left, the percentage or the area to the left of a -1. Okay, so that means if I went to the right, so keep that in mind, 0.1587, and then I'm going to come all the way over here to the right hand side, and I'm going to go to 1, and I've got 0.8413 because that's 00 right there. I'm following it down. 0.8413. All right, now I want you to see what's going on here, and this is really, really cool because I want you to see how things tie together. So when we looked up the z-score equals 1, we got the area to the left of 1 standard deviation from to the right is to the right of the mean is 0.8413. When we looked up the first z-score was z-score is -1. So that was 1 standard deviation to the left of the mean, and it was 0.1587. When we look for the area in between the 2 standard deviations, from 1 standard deviation to the right to 1 standard deviation to the left, guess what we get? 0.6826. And what does our empirical rule say? Approximately 68% of all of our data is going to lie between one standard deviation to the right and one standard deviation to the left of the mean. Isn't that cool? So let's continue that thought. Let's go to our table and look up -2.00 standard deviations, and we get 0.0228. Okay, and then over on the right, we're going to look up, here's 2.0, and then it's right up there is 00. Okay, so we're going to look up 2.00 is 0.9772. Okay, so likewise, we looked up z for -2. We did that one first, and that was 0.0228. And we looked up z as 2, which is 0.9772. And if we wanted to know the area under the curve in between z is 2 and z is -2, or standard deviation is 2 and standard deviation is -2, we've got 0.9544, and our empirical rule says approximately 95% of all of the data is in between 2 and -2 standard deviations. All right, so now we're looking at just using the standard normal table a little bit more. It says find the cumulative area that corresponds to a z-score of 1.15. So here on this table we have 1, but we want 0.15, so we're going to have to go over here. 1.1, excuse me. We've got to look at 1.1, and then we've got to go all the way over here to the 0.05. So since we're on the 1.1 row and we're over here under the 0.05, that should be the probability. Now remember, that's going to be to the left of that point. So to the left of the z-score, 1.15 is 87.49, or the probability 0.8749, or the area 0.8749. Okay, so it's showing that you're going to find the 1.1 on the left and then move across to the right, and you get the 0.8749. Okay, so now this one's a negative, and remember the negative ones are on the left-hand side of the page. So the negative ones in your book, this one's another book that you have to kind of watch these. They're not always the same in every book. Sometimes the negatives go in a different order, but as long as you will just find them up here, you'll be okay. This one is from a different book that kind of goes backwards on the left-hand side, but you're going to see different tables. You're just going to have to watch for them. So this one, -0.24, we're going to find -0.2. We're going to go across to 0.04, and we're going to have 0.4052 is to the left. Okay, so finding the area under the standard normal curve, sketch the standard normal curve and shade the appropriate area under the curve. Okay, find the area by following the directions for each case. To find the area to the left, we're going to find the area that corresponds to the z-score in the standard normal table. The standard normal table will always give us the area to the left. Okay, what if we want to find the area to the right? So in this case, it has the z-score is 1.243. If we go to the table, we're going to find that that corresponding area is 0.8907. Okay, if we want to find the area to the right, we're going to do the same thing, but we're going to subtract the area we find from 1, because the cumulative area is 1 all the way across, and so we already found out that the area to the left was 0.8907, and so we're going to subtract 1 minus 0.8907 to find the area in the little blue portion there to the right. Okay, if we're ever asked, and we will be, to find the area between two z-scores, we will find the area in the table for both of them and then subtract the two, just like I did on the example that I gave you on the board for 1 standard deviation to the left and the right, and 2 standard deviations from the left to the right. We're going to subtract the two areas to find the area in between the two, because the area given on the chart is always going to be to the left. All right, so here is just formats used for finding normal distribution areas. This is in your book, but just generally you're going to be using your TI 83 and 84 for almost everything. You're really not going to be able to use any of these on the test. Okay, now on the test you will have access to your table, and of course you will have access to your calculator. So we're going to be using those the most. All right, here's a generalized rule. The area corresponding to the region between two z-scores can be found by finding the difference between the two areas found in the table. Okay, don't try to memorize a rule or formula for this case. Focus on understanding by using a graph. Draw a graph, shade the desired area, and then get creative and think about a way to find the desired area by working with cumulative areas from the left. So basically, if we're trying to find the area in between, and we know that when we look up this value, it's giving us the area on the left, and then we look up this value, it's giving us all of this area, including this over here. We want the area in between. We're going to subtract them. Okay, so here's a good example. A bone density, mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these test results meet the requirements of a standard normal distribution. Okay, the graph of the bone density test scores is as shown in the figure. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So since we're looking at less than 1.27, we're looking at this probability is this whole area over here. And so basically, you got an 89.8% chance that this person's going to have a bone density less than 1.27, because that's the score in the table that corresponds to a z-score of 1.27. Okay, it says, note that the following are the same because of the correspondence between probability and area. So probability is 89.8, and the area shown in the figure is 0.8980. Area and probability are going to be equal. Okay, remember probability stops at 1. Area under the curve stops at 1. Okay, so now it says we need to find the area in the figure to the left of 1.727. So when we go to our chart, we've got 1.2. We go all the way across to the 7, and we get, I don't know if I can get you close enough to see it. No. There you go, 0.8980. All right, so now it says, Table A2 shows that there is an area of 0.8980 corresponding to Z is 1.27. We want the area below 1.27, and that's what the table is giving us. Okay, so 0.8980 is the answer. All right, so the probability that a randomly selected person has a bone density test result below 1.27 is 0.8980. Okay, or 89.80% of the people have a bone density less than that. All right, so now using the same bone density test, find the probability that a randomly selected person has a result above a -1, which is considered to be the normal range for bone density readings. Okay, so they're giving us a little bit of science information there. So -1 is considered normal. What is the probability that a person will be above -1? Okay, when we're talking about a z-score of a -1, okay, and the z-score of a -1, when we look at that on the table, -1 has a 0.1587. We already looked at that tonight. Okay, and so you're going to have, since we're looking at greater than, we're going to have 1 minus 0.1587, which is going to be 84%, 0.8413. So highly likely that somebody's going to have a bone density greater than a z-score of -1. Okay, because the total area under the curve is 1, we can find the shaded area by subtracting from 1. Okay, so 84.13% of all the people have a bone density level above -1. So now the last one is a bone density reading between -1.0 and -2.5 indicates the subject has osteopenia, which is some bone loss. Find the probability that a randomly selected subject has a reading between -1 and -2.5. Okay, so we're going to have to go here and look up the z-score for -1 again, which we already did. Look up the z-score for -2.5, which we would go to the table and look up -2.5 and find that value. I encourage you to do that on your own. The area between them is going to be the difference between the two. Okay, so 0.1587 minus 0.0062. And that's going to be 15.1525 when you do that subtraction, and 15.25% of the people have osteopenia. Okay, find the area under the standard normal curve to the left of -0.99. Okay, so we're looking at this. The left is what our table is going to give us anyway. Okay, we're going to find from the standard normal table that the area is 0.61611. Okay, so the area to the left is going to be 1.06. Okay. Okay, now we're doing, excuse me, I switched slides and didn't know what I was doing there. So this one is the one that corresponds to -0.99. Now let's go to the next slide. Okay, find the area under the standard normal curve to the right of z is 1.06. So now we're looking at this area to the right. We're going to go to 1.06, but we can't get this one right away. We're going to have to take 1 minus whatever we find in the table. Okay, so the table gives us 0.8554, which is to the left, and we're going to get 1 minus 0.8554, which is 0.1446. So the area is equal to 0.1446. Okay, the area under the standard normal curve between -1.5 and 1.25. So this is what we're looking for. So we're going to find the probability or the area under the curve for -1.5, find the area under the curve for 1.25, and subtract the two. Okay, so those are the values from the table, and we subtract them to get the area in between. Okay, so now we're working on finding probabilities. And remember, finding probabilities and finding the area is exactly the same thing. So we're going to say, but we should be able to do this from several different directions here. So probability and normal distributions. If a random variable x is normally distributed, you can find the probability that x will fall in a given interval by calculating the area under the normal curve for that interval. Okay, so right here they're talking about probability and area being synonymous when you're talking about the curve. So here we have a point here, 600, and we're saying the probability that x is less than 600 is equal to the area, and the area is what we find when we look on the chart. But remember, the table cannot be used here, because the table is only useful when our mean is 0 and our standard deviation is 1. So this is a normal distribution, but not a standard normal distribution. So in order to do this, we're going to have to transfer these values to a standard normal table. Okay, so that's what this is all about. We're going to sketch the normal curve, label the mean, any specific x values, and then shade the region representing the desired probability. So because we do not have a standard normal table, we're going to use this formula to turn it into these values into standard normal values or standard values, okay? And then we're going to use technology or our chart to find the area, okay? So we also need to note that the probability that it's between A and B, probability that the z-score is greater than a value, probability that the z-score is less than a value, are these notations here. All right, so going back to the problem at hand, we have our problem is the probability that x is less than 600. So we're going to use our z-score formula here, and we're looking for 600, so 600 will be our x. Our mean is 500, so that goes right there. Our standard deviation was 100, so 600 minus 500 is 100 divided by 100 is 1. So we're talking about a z-score of 1, and now that we have a z-score of 1, now we can use probability, the standard normal table. So they're showing you here that probability that x, the individual value, is less than 600 is the same thing as the probability that the standardized score z is less than 1. Okay, so let's do an example. What proportion of men are taller than the 72-inch height requirement for shower heads? Okay, heights of men are normally distributed with a mean of 68.6 and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head at 72 inches. So 72 inches is going to be our x value. Our mean, our mu, is 68.8, and our standard deviation is 2.8. So when we put this into our formula, okay, we're going to get our z-score being 1.21. Okay, and here is our work. We had the 72 shower head minus the mean over the standard deviation is 1.21. Rounded to 2 decimal places. So now that they've gotten the 1.21 z-score, now they can look up the 1.21 in the table 1.2. See if I can zoom in on this just a little bit here. There we go. Okay, so the z-score that goes with the 72 is 1.21, and then they're showing the calculation. So the technology. So now we're going to do it with the table and technology. So I'm going to show you how to do both of those. All right, so first we're going to do the table. We've got 72 inches is the shower head. We're trying to find the probability that a randomly selected person is greater than the height of the shower head. So we're going to say 72 minus the average or mean, 68.6 divided by the standard deviation. That gives us a z-score of 1.21. When we go to the A2 table, standard normal table, we get 1.21 corresponds to 0.8869, but we want the probability he is taller than the 72 inches. So we do 1 minus to get the area to the right, and that's going to be 0.1131. Now we're going to remember 0.1131 because what we're trying to get across here is that this was the table when we went to A2, table A2. We got the probability being 0.1131. Then we're going to do it with technology. We're going to say, hey, we get a little bit different answer. Technology is usually more accurate than the table is. Okay, so here we go with the technology. Okay, well, hopefully you can see my little calculator screen here. So I'm going to go over here to my second and my distribution. All right, and the second one on here is my normal cumulative, the CDF, just like we did the binomial CDF for a cumulative probability. The normal CDF is what we're going to use, okay? Now, when we click on the enter there, you may have a calculator that gives you some hints here. Mine does not. So what I'm going to do is I'm going to tell my calculator that I want to go from way to the left to the point that we're describing. Okay, so in ours, when we're using normal, we're going back to the 72 as being the point we're going to. We don't have to turn it into a z-score when we're using our normal CDF. So in order to tell my calculator that I want to take it from way, way ridiculously low, I'm going to put negative 1,000. You can even put negative 10,000 if you want. Okay, negative 10,000. Very, very low number. In other words, I'm going all the way as far left as I can. And then I'm going to put my rightmost number, which was the 72 inches. So I'm going to put my 72 here. I'm going to put my comma. I'm going to put my mean, which is 68.6. And I'm going to put another comma, and I'm going to put my standard deviation, which is 2.8. I'm going to close that. I'm going to hit enter. So it gives me 88.76 as my probability. But remember, that probability is the probability to the left. I want the probability he's greater than 72 inches. So I'm going to say 1 minus that probability. So second answer, this answer button down here at the bottom. If I do second answer, it gives me 1 minus answer up there, and I get 0.1123. Okay, so 0.1123 from technology. Let me write that down. All right, so we had 0.1123 from technology. So here we've got our board again. So let me zoom out to our board. So up there on the top right, we have our technology answer, 0.1123. Down there at the bottom, we've got our answer from our table, 0.1131. They are close, but they are not exactly the same. And that's because the technology is generally more accurate than the table. So there you have it. So here is that slide. Technology can be used to find the area to the right of 72 inches, and it becomes 0.1123. When we go to the table, we get 0.1131. The technology is usually more accurate than the table. Okay, so when we used the table, we found 0.8869, and we had to do 1 minus that, okay, to get the 0.1131. And when we did the technology, we had to do 1 minus that also, okay? So about 11% of the men will find the design to be unsuitable because they are taller than the shower head. All right, so on this one, we are finding probabilities for normal distributions. A survey indicates that people use their cellular phones an average of 1.5 years before buying a new one. The standard deviation is 0.25 of a year. A cellular phone user is selected at random. Find the probability that the user will use their current phone for less than 1 year before buying a new one. Assume that the variable x is normally distributed. Okay, so x is less than 1 is what we're looking for. 1.5 is the mean. And so now we're going to use the mean and the standard deviation to use our z-score. Our z-score gives us -2 standard deviations, which is going to be what we look up in the table. So we're given a value, -1, but then we have to put it into a standard normal value in order to be able to use our table. So z is -2 is what we need to look up. And when we do that, we're going to get 0.0228 as the probability that someone randomly chosen is going to get a new cell phone before 1 year is up. Okay? And the last one that we're going to do in this slide, okay, a survey indicates that for each trip to the supermarket, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes in the store. The length of time spent in the store is normally distributed and is represented by the variable x. A shopper enters the store. Find the probability that the shopper will be in the store between 24 and 54 minutes. Okay, so what we're going to do is we're going to look up x is 24 and we're going to look up x is 54 given the 45 minutes and the 12-minute standard deviation, and then we're going to subtract the two values that we get on the table. So we've got 24 to 54, so we're looking at that region right there. We put each one of them on our standard normal distribution. So the 24 corresponds to a z-score of negative 1.75, and the 54 corresponds to a z-score of 0.75. Then we take both of those to the table or else use our technology tool, and we find each one of those, and then we're going to subtract them to get the probability that there's a 73% probability that the person randomly selected is going to be in the store from 24 to 54 minutes. Isn't that cool? Okay, now if 200 shoppers enter the store, how many shoppers would you expect to be in the store between 24 and 54 minutes? So we found the probability of a random shopper was 73% probable of staying that time. So when we take the 0.7333 and multiply it by the 200 shoppers, and that would give us about 147 shoppers would be in the store from 24 to 54 minutes. Okay, it says find the probability that the shopper will be in the store more than 39 minutes. So now we're going to have to do a 1 minus, aren't we? So we're going to look up 39 as our x. We're going to find the z-score that goes with it is negative 0.50. We're going to figure out the probability is greater than by doing 1 minus the probability less than. So we find in the table that the probability less than is 0.3085. Now we're going to subtract that from 1, and we're going to get 0.6915 is the probability that the shopper will stay in longer than 39 minutes. If 200 shoppers enter the store, how many shoppers would you expect to be in the store more than 39 minutes? Okay, so we've got the probability of one shopper being in there longer than 39 minutes times the 200 is 138 shoppers will be in there longer than 39 minutes. Isn't that cool? Okay, so that's all we're going to do for this PowerPoint because I want to split these up. It takes too long to load them. So I'll come back and do the triglycerides on the next one, and we'll just divide it up here so that it doesn't take too long to load. And this is Mrs. A, and may God bless your day.